In this video, we'll take a look at section 8.3, which is on logarithmic functions. Now, our first objective is graphing logarithmic functions. So, a logarithmic function has the form f of x equal to log base a of x, where a is the base, and a is bigger than 0, and a cannot be equal to 1. So the equation y equals log base a of x implies that a raised to the yth power is equal to x. So I'm going to rewrite the equation in this form where my y is on the other side. So I have log base a of x is equal to y. Now there's a very important cycle that you should remember in order to change an equation from logarithmic form to exponential form. So you take your base, you raise it to this power, and it has to be equal to this expression. So it's saying a raised to the yth power is equal to x. Let's take a look at an example. So graph the logarithmic function. So we have f of x is equal to log base 3 of x. Now instead of having f of x, I'm going to change that to a y. So I have y is equal to log base 3 of x. Now I'm just going to rewrite this equation so my y is on the other side. That way it's easier for me to change it into exponential form. So I have log base 3 of x is equal to y. So I'm going to take my base, raise it to the yth power, and it has to be equal to x. So my new equation becomes 3 raised to the yth power is equal to x. Now let's go ahead and create a table of values. So we have our x, y, and now we're going to plug in some values. In this case, we're going to plug in values for y. It's much easier to figure out what x is equal to if we plug in values for y. So let's go ahead and plug some values in. Let's go ahead, let's choose 0, 1, and -1. So now, if I plug in -1 for my y, I get x is equal to 3 raised to the negative first power. I have 3 raised to the negative first. Now remember, whenever you have a negative exponent, you take the reciprocal and change it to positive. So I have 1 over 3 raised to the first, which gives me 1 over 3. So I have the ordered pair, 1/3 comma -1. Next, let's go ahead and plug in a 0 for our y. So we have 3 raised to the 0th power. So 3 raised to the 0th power gives me 1. So I have the point 1, 0. And now if I plug in 3 for my y, I get x is equal to 3 raised to the first power. So 3 raised to the first gives me 3. Okay, so I have 3 points. Let's go ahead and sketch the graph. So I have the point 1/3 -1, which is this point right about here. Then I have the point 1, 0, and then I have the point 3, 1. Now I could go ahead and connect these points with each other, and my graph is going to look like this. Notice that my x will never be equal to 0. The reason why is no matter what you plug in for your y value, you'll never get an x value of 0. So just like we were dealing with exponential functions, we had a horizontal asymptote. This time, with logarithmic functions, we have something called a vertical asymptote, where the graph will never touch the vertical asymptote or cross it. Let's take a look at another problem. So now we have f of x is equal to log base 1/3 of x. So let's go ahead, let's change our f of x into a y first. So we have y is equal to log base 1/3 of x. But now I'm going to rewrite it so my y is on the other side of the equation. So I have log base 1/3 of x is equal to y. So now I could go ahead and change this into exponential form. Take your base, raise it to the yth power, and it has to be equal to x. So I have 1/3 raised to the yth power equals x. Now let's go ahead and create a table. Let's plug in the same values for y. So we have 0, 1, and -1. So now if I plug in -1 in for my y, I get x is equal to I have 1/3 raised to the negative first power. Well, now that I have a fraction raised to a negative exponent, you flip the fraction, take the reciprocal, and change the exponent to be positive. Now 3/1 raised to the first power just gives me 3. Now if I plug in 0, I have 1/3 raised to the 0th power. 1/3 raised to the 0th power just gives me 1. Anything raised to the 0th power is equal to 1. If I plug in 1 for my y, I get 1/3 raised to the first. 1/3 raised to the first gives me 1/3. So let's go ahead and plot these points, and then we'll sketch our graph. So we have 3, -1, and we have 1, 0, and then we have 1/3, 1. Once again, we still have this vertical asymptote because our x value is never going to be equal to 0, or it'll never be negative as well. Now sketching our graph, let's connect our points. Let me try to draw that a little bit better. And we get our graph. Okay. So this was graphing logarithmic equations. So when you're graphing it, change it into exponential form, where you take your base, you raise it to the yth power, and it has to be equal to x. And then you just go ahead and plug in values for your y and figure out what your x is equal to. Now our next objective is converting from exponential form to logarithmic form, and vice versa. So very similar to what we just did when we changed our function into exponential form and then graphed it that way. That's essentially what we're going to be doing in this next objective. So we have 6 raised to the 0th power is equal to 1. So now in this case, our example is to convert to a logarithmic equation. So we're given an exponential equation. We want to convert this into a logarithmic equation. Okay. So converting it to logarithmic equation, we have log, and then our base is the same. So the base for your exponential equation and the base for your log equation are going to be the same. So I have log base 6. So we have log base 6 of 1 is equal to 0. Now if we do our quick little check, log base 6 of 1 equal to 0. Okay. Or you take your base, you're going to raise it to this power, and it has to be equal to this number, which is essentially what we have right here. 6 raised to the 0th power is equal to 1. So now we change from exponential equation to logarithmic equation. Okay. Next example, we're going to do the same thing. So we have log, and now our base here is 10. So we have log base 10 of 0.001 is equal to -3. If we did a quick check, remember you take your base, you're raising it to this power, and it has to be equal to this number, which is exactly what we had with our exponential equation. Next one, very similar, but now just dealing with a bunch of variables. We have m raised to the tth power is equal to p. So we have log base, and our base here is m. So we have log base m of p is equal to t. If we check using our cycle, we're taking our base m, we're raising it to this power, and it has to be equal to this p. This time we're going the other way around. We have a logarithmic equation. We're going to change this into an exponential equation. So we're starting off with log base 2 of 32 equal to 5. So we take our base, raise it to this power, and it has to be equal to this number. So we have 2 raised to the 5th power is equal to 32. Next one, very similar. We have log base 10 of 1,000 is equal to 3. Log base 10 of 1,000 is equal to 3. So changing it to an exponential equation, take your base, raise it to this power, and it has to be equal to this number. So 10 raised to the 3rd power is equal to 1,000. let's take a look at one more. So we have log base t of m equal to x. So once again, take your base, raise it to this power, and it has to be equal to this number. So we have t raised to the x power is equal to m. Now we just converted it from a logarithmic equation to an exponential equation. So this leads us to our next objective, which is solving logarithmic equations. When we start solving logarithmic equations, we're still going to be using the same cycle. We're going to change it into an exponential equation first, and then solve that exponential equation. So we have our first example, solve log base 10 of x is equal to 4. Well, let's go ahead and rewrite it. So we have 10 raised to the 4th power has to be equal to x. So 10 raised to the 4th power equals x. So our x is already solved. It's by itself. We just have to raise 10 to the 4th power. Well, 10 raised to the 4th power gives us 10,000. So we have x is equal to 10,000. Next one, a little bit harder. We have log base x of 81 is equal to 4. Okay, so let's rewrite it so it's an exponential form. So we're going to take our base, raise it to the 4th power, and it has to be equal to 81. So we have x raised to the 4th power is equal to 81. Well, now if I want to solve for x, I have to try to figure out, okay, x raised to the 4th power. So what number raised to the 4th power is going to give me 81? So I can get rid of that 4th power by taking the 4th root. 4th root and that 4th power cancel out. I get x is equal to, now the 4th root of 81 gives me 3. And you can do a quick check. Well, 3 raised to the 4th power, that is equal to 81. Okay, next problem. Log base 2 of x equal to negative 2. Okay, so let's begin by rewriting it to exponential form. So take root 2, and you take 2, raise it to the negative 2nd power, and it has to be equal to x. So we have 2 raised to the negative 2nd is equal to x. Okay, well, our x is already by itself. We just have to simplify the 2 raised to the negative 2nd power. Now, going back to our rules for exponents, if we have a negative exponent, we have to take the reciprocal of 2, which is 1 over 2, and then you change the exponent to be positive. So we have 1 over 2 squared is equal to x, which is telling us that x is equal to 1 over 4. Okay, now this takes us to our last objective in this section. This is the basic properties for logarithms. So our first property, log base a of 1 is equal to 0. So no matter what your base is, whenever you have log of 1, this is always equal to 0. Reason why, so if we used our property, if we change this into, an exponential equation, you take your base, you raise it to this power, it has to be equal to this number. Okay, so you have a raised to the 0th power, this has to be equal to 1. So in order for you to get 1, you'd have to raise your base to the 0th power. So that's why log base of 1, this is equal to 0. Next, log base a of a, this is equal to 1. So if we use our cycle to rewrite this into exponential form, you have to raise your base to the 1st power in order to get that same number. So a raised to the 1st power is equal to a. Okay, so now we could use these properties to simplify logarithmic expressions. So for example, log base 7 of 1. Essentially what I'm trying to do here is I'm trying to figure out 7 raised to what power will give me 1. Well, I know I have to raise 7 to the 0th power. 7 raised to the 0th power gives me what? So 7 raised to this power has to be equal to this number. Okay. And that's just using our first property here. So take a look at another one. Log base 2 of 2. Try and figure out 2 raised to what power will give me 2. Well, using our property, this has to be equal to 1. 2 raised to the first power will give me 2. Next one, log base c of 1. Well, what do I have to raise c to in order to get 1? This would have to be 0. C raised to the 0th power will give me 1. And now this leads us to common logarithm. Common logarithm is when your base is 10. So log base 10 of a, this is just equal to log of a. So in other words, when your base is 10, you don't see the base written out. You'll just see log and then of some number. So we just have log of a. So when you have common logarithm, when your base is 10, you won't see it written out. So for our next example, find the common logarithm, round to 4 decimal places. We have log of 22. Notice how we don't have a base written out here. If we don't have a base, the base is really 10. It's really log base 10 of 22. So now on your calculator, you have 2 logs on your calculator. One of them is the common logarithm, which is base 10. And then the other one is natural log. You'll say ln. Okay, so over here we're dealing with base 10. Now just to give you an idea of what we're looking for here, we're trying to figure out what number, so 10 raised to what number will give us 22. Well, we can't raise 10 to a whole number to get 22. Okay, so what we have to do here is we actually have to use our calculator to figure out what this is going to be equal to. So using our calculator, we're going to put in log of 22. Okay, so let's see what that gives us. Okay, and it's saying to round to 4 decimal places, so we have 1.3424. So we'd have to raise 10 to the 1.3424 power in order to get 22. Yeah, so since this isn't a whole number, we actually have to use our calculator to figure out what this is equal to. Next one, log of 1,278. Remember, keep in mind, since we're not given a base, our base here is 10. So we're trying to figure out 10 raised to what power? 10 raised to what power is going to give us 1278. Well, this isn't going to be a whole number, because I know 10 raised to the 3rd power gives me 1,000, and 10 raised to the 4th power gives me 10,000. So I know it has to be a number between 3 and 4. Okay, but let's get an approximation. We're round to 4 decimal places. So we have log of 1278. Okay, we get 3.1065. Next one, log of 100. Remember, our base here is 10. So we're trying to figure out 10 raised to what number will give us 100. 10 raised to what number? My computer's kind of acting up. So 10 raised to what number will give us 100? Now in this case, we don't actually have to use our calculator for this, because we know we could raise 10 to the second power, and it'll give us 100. So log of 100, this is just equal to 2. If you put this into your calculator, you get the same result. Now last example, we have log of -3. Trying to figure out what this is equal to. So remember, we're not given a base here, so our base is really 10. We're trying to figure out 10 raised to what number will give us -3. Okay. Well, for this particular problem, this is actually undefined. The reason why is because there isn't a number I can raise 10 to in order to get -3. No matter what you raise 10 to, so let's say I raise 10 to the negative, I don't know, say 4th power, this is always going to end up being positive. This would give you 1 over 10 to the 4th power. 1 over 10 to the 4th, this gives you 1 over 10,000. So no matter what you raise your 10 to, whether it's a negative number or a positive number, this will never be equal to a negative number. Also, it'll never be equal to 0. So whenever you have the log of a negative number or the log of 0, this is undefined. Okay. So if you have, say, log base a of 0, this is undefined. Also, log base a of, say, some negative number, this is also undefined. Okay. And the reasoning behind it is because you can't raise your base to some number and it gives you a negative result. Same thing with 0. You can't raise your base to some number and it gives you 0. Okay, so those two log functions, those would be log expressions, those would be undefined. Okay. So that was it for section 8.3. If you have any questions, just email me and I'll help you out.